Okay, hi everybody. This is lecture 4 in Ramanujan Explained. This is about entry in chapter 16 of Ramanujan's notebook, and it's a useful transformation formula. So, okay, this is what it looks like. So, on this side, so there's a 2 phi 1 here. So this is a 2 phi 1, some products, and this is 2 phi 2. So 2 in the numerator, 2 in the denominator. And it's one of the standard formulas. And the last time what we did was oops, for some reason I'm unable to control it as well as I'm usually able to. Okay, let's show this. So So the last time we proved the first formula over here using what is called Heine's method, and this time it's about a minor modification in the technique. But before that, let me just introduce the exercises in chapter 3. So first thing is that we can iterate. So we can apply this 2 phi 1. So it's of the form 2 phi 1. So the formula which we had was of the form 2 phi 1. 2 phi 1 is equal to some products times 2 phi 1. And we can, so this is this one. And we can iterate it. So we can interchange the roles of, you can put this as A, this as B, and get something else. And then again, interchange it and get B. So these are called iterates of Heine transformation. And these are also very useful transformations, which Ramanujan used many times, but apparently did not explicitly write down. And uh, a minor variation of the technique leads to this identity right here. So this is also a problem. This has got, if you look over here, it has got a q raised to the power h and a q raised per t. And here there is some interchange. So there's a t times j in this. So typically Ramanujan used h equal to 2 and t equal to 1, or h equal to 1 and t equal to 2. And h equal to 1 and t equal to 1 is Heine's transformation. So this is Heine. And this formula in general appeared somewhere in 1966 in Andrews' papers, but it wasn't highlighted. It wasn't written like this. It was in a very weird way. And he only had it for h equal to 2 and t equal to 1 typically later. But somehow if he missed this one, and if you do h equal to 1, t equal to 2, a lot of these things just a lot of the formulas of Ramanujan just fall out as equal. So all of them can be obtained by Heine's method. And if we rewrite this in the form of Ramanujan's entry, then it will help you in doing the homework problems. So I should mention that when we are writing, when we have h is a complex number, then we are basically, so this is defined to be aq infinity over aq to the h q infinity. And here, absolute value of q is less than 1 for convergence of these products. So h could be anything. H could be a complex number for all we get. And here, of course, we're using h equal to 2 and t equal to 1. But so this is defined if it's 2 or 1, but it's true for any complex numbers. And um, So for these series, you want these guys to convert, these guys to be less than absolute value one to converge, and for these infinite products, you want the absolute value of q raised per t to be less. So this condition comes from these conditions come from the products, and this condition comes from the sum over here for convergence. And this is very minor variation of Heine's transform. Somehow this has been missed, and um, it's easy enough to do a new one. And I'll just give a sample of the identities which Ramanujan has. So here is a sample. Oops. So this identity, then there is entry. So these are all entries in the lost notebook. And this one, so for some reason, he just takes certain kind of, special cases. And if you take special cases, you get lots and lots of his identities. So if you recall, Ramanujan wrote his results uh, in a notebook and didn't include proofs. And he may have got the proofs at different times. So it's very possible that uh, he had this kind of thing in mind, because these things came very close to each other. So already we have covered all these entries now in this chapter. So there are quite a large number which just follow from Heine's method and its special cases. So we are well into Ramanujan's entries now. Now let me show you. Let me begin the lecture. So I'm sorry if there's something wrong with something which I've done. Which has messed up my I'll seen it later. Let me write it down. So one item I should mention, which is very useful, one item which is very useful in taking these special cases is this limit as a goes to infinity. So if you have a q, well, if you just have a sub q to the k and divide by a to the k. So this limit, so we're taking this limit. This we take a lot. So limit as a goes to infinity, and the top part is 1 minus a, 1 minus aq, and so on up till 1 minus aq to the k minus 1. And then we are dividing by a, so all these are divided by a. And then, so this you'll get minus 1 to the k, and you'll get q raised to the power 0 plus 1 plus 1 up to k minus 1. So this is somewhat, trivial limit, but we use it a lot. K choose to. And this is this is always there in hidden form in a 2phi1. So now let me write down in entry entry. So volume 3 again of Ramanujan's notebooks. This is the entry. So aq infinity divided by bq infinity is equal, times the sum k going from 0 to infinity c b by a q k q t q k. A raised power k is equal to m going from 0 to infinity b by a b by c q k q d t q k minus 1 raised power. Okay, so this should be m q raised power m choose 2 and ac raised power m. So okay. So this side has this kind of 2 in the numerator, 2 in the denominator, and this guy, and this is a 2 phi 2 here. And if you remember this 2 phi 2, RPS has a minus 1 raised per m, q raised per m by 2 raised per something factor. So this is where that is. And this is some products times 2 phi 1. So this is entry 16.8, and let me just prove it. So prove. So last time we again considered this product, this sum b by a c q k. So this guy q d q sub k a raised per k. So we had considered this for the 2 phi 1, and in Heine's case, so in last time we took CQK over DQK. So we expanded it in terms of CQ infinity over CQ to the K, Q infinity, and so on. And DQ infinity, DQ to the K, Q infinity. And then these two terms over here, we expanded using the binomial theorem. And then we interchange, right? So this time, the difference is that we expand CQK over DQK as a 2 phi 1. So we expand using I don't know what to do. Okay, this is better. Okay. Some new feature. So we are going to expand this, and we use this um, identity which we did last time. So d over c, d q cq to the k. So this is from using an identity last time where we said, okay, so this was the identity. Q raised power minus k, b c q, and cqk over b. This was equal to c over b qk and cqk. So this was a terminating special case of Q Gauss. It was also called Q Chu van der Monde. So this was one of the corollaries. So instead of using this infinite product, we just use this uh, to expand these terms in Ks. So K going from 0 to infinity, B over A, Qk, Q, Qk, and A raised per K. And then I'm expanding this from using this chap, and I get Q raised per minus K, then D over C, Qm, and Q and TQ sub, and CQ to the K raised per M. Right, so this is what we get, and this is of the form. So here is the magic trick. This is of this form. And what we are doing is just making pictures like we do in calculus. So this is M, this is K. This is K equal to M. What we are doing is we are doing K going from 0 to infinity, and M is going from 0 to K. So we are summing like this. So this line is K equal to M. And what we want to do is we want to interchange the sum. So what we do is we have M here and K and this picture, and we start going like this. Right. So this is this guy. If you write the same thing, you will get M going from 0 to infinity now, and K is going from M to infinity, AKM. And this chap right here, we can write it as M going from 0 to infinity, K going from 0 to infinity, AK plus 1, M. So why K plus M? Because when K is 0, then you get AM, and you're starting with AM. So when K is 0, you get M plus 1. So this is just Cauchy's product in reverse. But somehow this seems to work a lot, and this is in fact what Wilf. So Wilf calls this the snake oil method. So snake oil is supposed to cure every disease. So Wilf felt that this cures everything, and we use it a lot in our work. So now what is S? So if we just interchange this guy, so S becomes M going from 0 to infinity, D over C, QM, and QQM, TQM, C raised for M, K going from 0 to infinity, P over A, Q K plus M over Q K plus M, and we have Q raised for minus K minus M, Q M K, no M, and A raised for K plus M. So just see, we have 4 terms here, right? So these 4 terms come here. This guy, this guy, this guy, and this guy will come outside, and that's fine. And this and this and this depend on K, so 3 terms, and there is an additional power of Q which I've forgotten. So it's over here, it's Q raised to the power k plus m. M. Right, so we simplify this. How do we simplify? So, so simplify a little bit the inner sum. So first thing is that p over a q k plus m. Uh, we, we write it as p over a q m. So first m terms and then the rest the k terms. And b we use this uh, identity which is formed by reversing the products and just multiplying and dividing by the right thing. So this is one of the elementary identities. Q raised power k choose 2 minus mk. And this one we will use with n going to k plus m and k going to m. And if we do that, we'll get q raised power minus k minus m qm. This is equal to q. So k plus m on top and k plus m minus m at the bottom. So you get k and you'll get minus 1 raised power m q raised power m choose 2 minus k plus m times m. So a lot of things cancel. So if you compare some things cancel. So we're using this over here. So one of these things cancel and this cancels and you get these extra terms which are in terms of m. So I'll just write down what you get. So we get S is equal to summation m going from 0 to infinity d over c e over a to m u t u m a c raised for m minus 1 raised for m q raised for m choose 2 and k going from 0 to infinity bq to the m over a q sub m uqk uqm. So there's something wrong here. It should be bq to the m choose k here. And there's a q q k plus m which cancels with q q k plus m. So this gets cancelled. And there's a raised for m. And now this chap is a 1 3 0, so you can apply the q binomial theorem. So this is bqm over a times a q infinity divided by a q infinity. So this can be some. So the idea of the idea is the same essentially, except that we are using something else. And now we can bring this outside and we can write this guy over here. So I get, let me just write it down. So I get PQ infinity. I'll just explain how I got that. AQ infinity, sum m going from 0 to infinity, P over C, P over A, QM. So this AQ infinity has come out, and this BQ will be here. And we have AC to the M minus 1 to the M, Q raised per M. So this part right here, this one right here is just pq to the m q infinity, and this can be written as p q infinity divided by bqm. So the first m terms cancel, and we get this. So this part here, it gives you this term, and it gives you this guy, and rest was all there. D over c, b over a, q, d were all there. All these things were there already. This should be m. Right. So this proves it. This is the proof. As you can see, it's very mild modification, but it works. So just to yeah, just to summarize, now it's very small, but you can see that all we are doing is we are writing a ratio of two of these terms as a 2 phi 1 instead of a instead of a 1 phi 0, and interchanging the summation using this technique. And again, this technique is super useful, so you'll see it all over the place. The technique of just interchanging the sums, and then just simplify and get whatever you get. So it's really a derivation proof. It's quite simple somehow. Uh, this identity, uh, there are all kinds of vague proofs which are given, but one of these proofs is this one in Bruce Burns' book. So it has many proofs which are given there, but this is a simple enough proof, and it follows very simply from our technique, Heine transformation. So let me list some corollaries. So this is the next identity, entry. So chapter 16, entry 3 dot dot um, sorry, volume 3, chapter 16, and then 9. So this is aq infinity times q raised per k square e raised per k over q aq qk, k going from 0 to infinity. So I should at some point stop using this sub q. K raised per k, q raised per k, k plus 1 over 2. So how do we prove this? The proof is quite easy. Uh, I'll just indicate some of the I mean, just the details and just the outline, and you leave the details to you. So in the previous entry, you take d going to 0 and a going to 0 as a limit, and then replace c by b. And then we'll get following, we'll get 1 over b q infinity, summation k going from 0 to infinity, c over b qk qqk minus 1 raised per k, q raised per k, k minus 1, b raised per k is equal to m going from 0 to infinity, q raised per k square minus, okay, let me just use k, e raised per k, and b q raised b comma q qk. So you get this, and then all you have to do is relabel and replace C by BQ and B by AQ, and you're done. So this gives you the gives. So that's corollary 1. Corollary 2, this is entry, another one of his entries, P.16.3. And also in the lost notebook, it comes up again. So in the lost notebook, he is for some reason looking at the transformation theory of 2p1 type series. And we will at some point see what the reason is. And the reason has to do with Ramanujan's later work in mock theta functions. Anyway, so this is k going from 0 to infinity, q raised per k square a raised per k divided by q a q sub k is equal to 1 over a q infinity. So this is a summation theorem, and the proof is very simple. You put B equal to A in corollary 1. And there are two more corollaries, two further corollaries. Of entry 16.9, and these are mentioned in Ramanujan's notebooks, and these are as follows. So Q's. So now I'm using, I'm suppressing the Q. So A sub infinity is the same as A Q sub infinity here. K going from 0 to infinity, q raised per k, k plus 1. And this is q, k square. And is there a 2 there? So, I'm not sure about this. I'll check. But I think there might be a 2 here. So this should be equal to minus 1 raised per k, q raised per k into k plus 1 over 2. Yeah, gone green. So the proof is I mean, you can say it's an exercise. Let me put it this way. So you just you just take a special case here very quickly and get the answer. So these are in entry 9. So these are corollaries of entry 9. So this one. Oops. So it's of this guy, of corollary 1. So it's corollary, it's an entry of here. So you put P equal, sorry, you put, I mean, you get rid of a lot of stuff and you get this. And the other one is back to this notation, q square infinity, k going from 0 to infinity, q into k, 2k plus 1. um, Q raised per k square. Okay, again, proof is a exercise. So you have to check whether this is divided by 2 or not as part of the exercise. But the real question is why these special cases? So the real exercise is, real question is why these special cases? So this is one of the mysteries that we need to answer. And I mean, one of the reasons is that if you look at this, this is a triangular number. So q raised power a triangular number. And this is q raised power a square. So these are not precisely generating functions of q raised power k square, but alternating over there. So slight variation on the classical theme. And this is something which attracted Ramanujan. So a lot of his special cases seem to be hanging around these kind of guys, and we'll see a lot of we will see more about these things as we go along. So yeah, that's it to summarize. So that's it for this lecture. To summarize, we have just just a minor modification of Heine's method, and in this modification we use some other identity to expand the inner sum, and this is organic. You can do it for any identity that you've got. You can expand it and keep going. So for somebody who's an somebody like Ramanujan, who's an inventive genius, this is something which you would have tried. And what is interesting here is that he has also uh, taken some special cases when he does that. And somehow this is the second round of Ramanujan's organization. So he has put simpler identities first. So it's clearly he would have got uh, identities, the bigger ones first, and then taken special cases. And he put one of the small special cases over here, and all these identities show up in various forms in his continued fractions. So it's not that he was just doing it just for the heck of it, but these were showing up multiple times in his work. And what I want to do next time, so we have already got we've got a bunch of identities, and I'm planned to put some more exercises in this chapter, in this lecture, after this lecture, which include many more of Ramanujan's transformation formulas from the Lost Notebook and here, and we will now go to the next technique, and that technique involves taking limits, and that involves doing some little bit of background work on infinite products. So the plan now is to spend a lecture on infinite products, maybe, and the goal is, so the goal here is to define what is called so little bit of infinite products. So the goal is also to define what is the Q gamma function. And that will help us take some limits. So that will help. This will be for taking limits. It will help us take limits as q goes to 1. So we already have one limit for going to 2 goes to 1. So if we can do, if you take limits, if we can take limits of these infinite products somehow, and taking limits of the infinite sum is easy, then we can get we can try to examine what of the hypergeometric theory Ramanujan had. So that will cover a lot more. If we get this technique in, it will cover a lot more things. And this is also required somehow now. I mean, it was already required, but this will also help us understand some other set of the next set of Ramanujan's results, which are about bilateral sums. So there's some more facility about the analytic properties are required. So we will do some products. All right. So that's what I had for the day. Any questions?